I'm going to try not to double cover too much. I know that kind of gets hard for everybody. So with any system, you have to have an intake filter, period, end of. Why? You have to have an intake filter to make sure that particulates do not enter your system. Okay, just like your oil filter on your car, just like your air filter on your house. You do not want crap getting out of that filter and getting into your system, right? You have to have a pump or compressor. Pump, of course, is hydraulic, compressor is pneumatic. You have to, so this is something that is drawing and moving your fluid, right? Now these next two are kind of a optional. You have aftercoolers and dryers and receivers. You don't have to have these. Okay, you don't have to have them. They're nice to have. They're extra you can have. Don't have to have them. And they do exactly what they sound like. Aftercooler is going to take any fluid that is overly hot, excuse me, and cool it down to a better level. Why do we want to do this? Well, because if you're in some place like Arizona where it's 120 degrees all day long for over a month plus, by the way, yeah, that actually is something they deal with. You know, you don't want hot air in your system because that can actually cause what? Cause heat stress to your parts, right? Not a good thing. Have an aftercooler. Dryers. Why would we want a dryer in anything to deal with Alabama? Humidity. Humidity will kill all your components faster than you can say oops. That's why we have so many ways to pull water out of the air. All right, you have the receiver, which is a vessel to hold things. You have the pressure regulator that is required. Why? Because we don't want unregulated pressure in our system. We could possibly blow seals doing that. Pressure regulators are our friends. Oilers, that's another thing that is almost strictly pneumatic because hydraulic provides its own lubrication. However, pneumatics does not. And what can happen to parts if they're not lubricated regularly? Seize up, corrode, break down, have all sorts of issues, right? That's why a lot of systems have oilers. Not all, but a lot, is to make sure that oil goes back to your components. So something like your cylinders and such, it keeps them oiled up from the inside of the system. Because let's face it, who wants to try and go to a giant pneumatic motor and put oil all over that thing? Anybody want to volunteer that nasty job? If you're paid hourly, yes, you might be up for that. Otherwise, having a way to distribute it in a fine mist works a lot easier, better, and you don't have to get nasty for it. Piping is a must because we got to get we have to have some way to get it from one place to another. Let's just put it that way. Control valves, we have talked a little bit about it. We've talked about directional control valves and flow control valves. Some of y'all have actually gotten that far in lab. It's kind of fun, right? By the way, we do have more labs. I got them run off today, so we will be talking about those later. So a lot of what we have to deal with are things like actuator orifices and the volumetrically how much they have to deal with. So we'll talk more about that here in just a minute. So actuators, we have two main categories of this, and that is cylinders, which y'all have dealt with, and rotational, which you've dealt with one type of it. We don't really deal with the other type, but that is something that you will see in field. So cylinders are linear. They run straight lines. These are one of the most common things you will see. Why? Because making things run in straight lines is very easy, right? And when you're doing production, running straight lines is a very good thing to do. And then we have rotary. These convert everything into a rotational motion. You have the rotary that are partial rotation. Those work just like your rotary phone. Everybody remembers those? Where you put your finger in the number, you swiped it all the way to the end. When you let it go, it sprung back. You had to do that over and over again to make a phone call. Anybody seen those? At the very least, you've seen them in a movie, right? And then you have motors. So rotary has a limited stroke. Motors, as y'all have seen in lab, have unlimited strokes. Basically, they just spin. Okay. Now, that's great if you need a perpetual spin. However, if you need a limited spin, that can be a little bit harder to deal with, right? So parts of a double-acting cylinder. So double-acting cylinders are quite normal to have on a lot of places because we can control them very easily. Now then, if y'all will remember, we talked about the fact that you have space in front of and behind. What do you think this is right here? So we've talked about it more than once. That is your what? That is your piston, right? That is your piston right there. That is what you calculate area for. That is your bore. This is your rod. So whenever you're looking at this, you can see how much area that rod takes up. That's why when we're doing the math for it, what do we have to subtract for? Subtract the area of the rod from the area of the bore, right? We'll work on that when we review for test 2. Okay. You have seals all in this. Why? Because you don't want your fluid leaking past it. It kind of be a bad thing because you break the seal, you are in some deep trouble. You have rod wipes. Why would we need rod wipes? Well, because if we have a big, dusty, dirty environment out here, we do not want this thing right here scratched. We do not want the seals breached. So we find ways to keep the rod clean because that keeps things out of your fluid. It keeps things out of your cylinder. It makes it last longer. The longer we can make them last, the better, because these things, the bigger they are, the more expensive they are. And replacing them is a real pain. It's manufactured, so the manufacturer is going to pick and choose what they use. This is hydraulics and pneumatics. They both use the same kind of tech. Yep. For anything that you have a hydraulic or pneumatic cylinder on it, you don't want those cylinder rods scratched because that introduces contaminants into your system. The more contaminants in your system, the more trouble you're going to have with it. So that is why these things are sealed 7 ways to Sunday to prevent contaminants. Okay? All right. So, double acting cylinder, put pressure in one end, it moves one way, put pressure at the other end, it moves the other way. Now what it's not showing you is the fact that this fluid, the blue fluid, just because you remove pressure does not mean that fluid is not still in there. Y'all saw this with meter in versus meter out, right? That fluid is still in there and held to pressure until it is released. Does that make sense? We saw this with meter in versus meter out. With meter out, that pressure does not release until it's gone through the what? Is it going through the check valve or is it going through constriction? It's going through the constriction on meter out. On meter in, it goes through the check valve to release. And that's why whenever you're doing meter in, it will not, if you put pressure anywhere near the opposite direction, then it just releases and it'll go. It builds pressure slowly, which means that it can slowly build pressure up and push, and it can have a good steady push because it's dumped all the air out in the front of it. Meter out, you have, if you put a meter out on both sides of this cylinder, you have full control of extension and retraction. There is no way it's going to slide either way without your control of it. Does that make sense? We do check valves to create that control. All right, we have double-ended rods. You know, they do exactly what they say. They have 2 rods ends. So whenever you're calculating area of these, you have to subtract the rod end for both sides of the bore. So these push as well as pull. Okay. Well, technically they both, never mind, I'm not gonna say it. Leave it right there. All right, so single acting cylinders. These can be done in a multitude of configurations. Why? Because there's multiple ways we need them, and they're great for when you want to put pressure on one direction, and then when you release pressure, let it come back on its own. These are a great candidate for meter in, right? They're great candidates for meter out too, but they allow pressure to push up, and then you can put slowly descend it back, or you can just tell it to come on back as it goes, depending on what you want to use. So you have load return, spring return, which you've been using in lab. You have hydraulic or pneumatic rams, which do exactly what you think they do. And you have telescoping, which any of you have ever used the little plastic lightsabers that you can get at Walmart, y'all know what telescoping is, right? Because all you gotta do is pop that thing out and it is able to extend. And you put, exactly, you retract by pushing it back in. All right, so any questions on this, guys? Like I said, we've used these in lab, so I'm not. So you have your spring return, you have your telescoping. When pressure is removed, they retract. When pressure is added, they extend. Simplest acting, single acting cylinder. You have the 2-piston cylinder. These remind y'all of anything? Anybody's ever worked on their brakes? This is the wheel cylinder, right? What does it do? You apply pressure with your foot to that brake, and this immediately puts pressure out to your calipers, right? I might be putting out the wrong part on that. I'm sorry, I'm not a total expert on the names of brake parts. All right. So with this one that's showing you a couple of different ways it can work, you have air or fluid in this, and whenever you put pressure on A, the fluid on the inside immediately dumps out. However, if you have one blocked, it's going to put all the pressure to the other side, the one that's blocked. So one of the things we have issues with, and this is one of those things that I like to say robots are better at than humans, is seals, right? Because humans, how well can we pour a seal? Y'all know what I'm talking about? Take a gasket seal fluid and try and trace around every place that needs that gasket seal. How well do we do? How precise are we? We're not very good at it. And that's why we generally, for anything that has to be sealed, we tend to let a robot do it. There's a lot of different piston rings. They come in all shapes, sizes, depending upon the needs of the customer, right? So the caps are the main part that on the outside we use to, great, now I can't speak. These are the part of the rod that actually has the ability to do the work. Okay, this is the part of the rod that sits on the outside permanently. So this is where we tend to screw on attachments so that, and a lot of it's screwed on. Why? Easy to be replaced if necessary. If the head wears out, breaks, or anything like that, we can just unscrew, put a new one on, done. We can weld it and press it on there, but those are non-repairable, which aren't as generally desirable because that's going to take more work to make another one ready, right? And not to mention, you also run the risk of what? If you weld or press them on. Damaging the rod. Well, if you're not gonna have putting a hole in it's bigger one right there. Damaging the rod or putting a hole in it, damaging the cylinder itself. Yeah, not something you want, right? So I'd say a good 90% of these are screwed on just because of A, convenience, B, ability to change things out, and C, run less risk of damage by an improper weld or a not so well done press. All right. You also have to think that these things are only as sturdy as they appear. You start pressing anything on this, you run the risk of damaging some other part of it. Right? If you crack the casing on this, it's done. All right, and then you have mounting. Mounting, there is no way to describe the different ways that this can mount because they are as many as an engineer can think of. Right? They can be mounted in 1,001 different ways. Heck, I've seen these things mounted just by screwing the rod into something so that you have multiple cylinders actually pushing a whole plate to move it. And that's actually one of the cooler ways I've seen this used because it's used as a injection molding release. It forces the part off the injection mold. I've seen it used that way. So as many ways as you can think of to mount it, there are ways to mount it. It always depends upon what? Application, engineer. You know, what are they calling for? What are they thinking they need to do with this? It's up to us as the people that actually have to work on this to sit there and go, yeah, no, that won't work. All right. So I'm not going to go too deep into mounting because there's just too many different ways you can mount this, depending upon the job it's trying to do. That's going to be the main way you determine how anything is mounted is what is the job it's meant to do. So you've got cylinders performing work. You've got the cylinder being able to push a 4,000 pound load, and it is mounted in a horizontal position, and it has an ability of the travel versus the workspace it's moving it to. So what do we have to kind of keep an eye on with something like that is exactly how far that rod extends, how much weight can that rod enforce. That's going to be a big one, right? That's kind of like how much can I move with just one arm? Because what is the skinniest part of a human? Your one limb, right? Versus moving your whole body, you're moving one limb, right? So the amount of force you're able to push behind your hand is all dependent upon the arm that's with it. The same thing with a cylinder and a rod. That rod can only push so much. If there's any kind of a crack in it, if there's any kind of a bend in it, if there's any kind of weakness in it, what can we do if we overstress that rod? You're going to break it. The simplest answer of that is you'll break it. And then you'll have to replace it. Reinstall, re-engineer, recall if you're making multiples of these. So just kind of keep that in mind when you're looking at these. So some of these come with their own check valves. Why? Because we don't always want the air running straight out of these. And it can allow for a secondary port to allow for excessive air to come out if it's necessary and there's too much trying to talk too fast. So check valves, you have bushing sleeves, you have what's called a cushion port. Now, what do you think a cushion port is for? Cushion what? Slow it down. Why would we want to slow it down? Because just, wear and tear. Because just like a soft closed drawer, why do we want those installed these days? So you're not slamming it and breaking it down over time. Has anybody ever seen what happens to a drawer over time if it does not have the soft close? It warps like crazy. What does it do to the rails? Tears them up. What does it do to the back of the drawer? Breaks it down. So one of the things they do with cylinders is they put that cushion port on most of these so that instead of every day, all day long, to where it's breaking down the bits of metal into it, which isn't just bad for your cylinder, it's also bad for your fluid, right? Because what is your fluid constantly pulling away with it now? Little flecks of metal. What's that going to do to your piping? It's going to cause it to wear and tear faster, right? What's it going to do to the ports that it has to flow through? It's going to tear that up. What's it going to do to everything? It just you're having to kind of look at what is the wear and tear aspect of this. So cushion ports have been added to a lot of these to prevent that. It's kind of like these days, I don't think you can buy a piece of furniture with drawers that are not soft close at some way or another, right? Because it prevents the wear and tear, it prevents warping, it prevents a lot, it makes it to where it lasts as a longer product. There you go. So the cushion does exactly what you think it does. It works just like meter out, it just keeps it from slamming back. Okay? I'm trying not to push this too much. All right, so controlling the speed, and this is something y'all have done in lab. So you're looking at the volume of fluid needed by the cylinder per stroke and the flow rate of the fluid. What do we mean by that? Well, in other words, if we constrict the amount of flow into the cylinder, right, we control the speed, okay? Or another way you can put it is the bigger the cylinder, the longer the bigger the cylinder, if your valve is not big enough to have the fluid flow at a certain speed, the slower your cylinder will extend. Does that make sense? Did that actually make a whole sentence? The bigger the cylinder, if your ports are not big enough with that cylinder for the speed you're wanting to achieve, it's going to be that much longer for it to extend or retract. So a lot of this is determined by the fact of how big are the ports on the cylinder. The size of the cylinder is probably one of the biggest things of all, though. Why? Because if you have a 10-inch bore versus a 2-inch bore, which one's going to fill faster? The 2-inch, as long as the port sizes are sized correctly. If your ports are undersized, or let's say constricted by a flow control valve, I can make it to where that 2-inch cylinder extends slower than the 10-inch, right? So you have your flow rate is equal to your area times your length divided by your time. Or you can even say time is your area times your length. Length is referring to the stroke length. So if you have that same 2-inch cylinder, but it's got a 12-inch stroke to extend to, you got a 10-inch cylinder with a 1-inch stroke, which one's likely to be faster? It's going to be dependent upon the size of the port and how long it takes for it to fill, right? That flow rate is key on this. Does that make sense? So speed, the volume of the cylinder cannot be changed once it is created, right? A 10-inch cylinder with a 1-inch stroke cannot be changed to a 10-inch cylinder with a 6-inch stroke. It's not going to work, right? It is what it is once it is made. All double-acting cylinders with a rod will retract faster than they will extend. Why? And we've kind of gone over this. Volumetrically, which one has less volume to fill? The rod side. Why? Because it's got the rod, right? Less area. Does that make sense? Kind of like what's faster to get across, Texas or Alabama? Less area to cover in Alabama. Just to put it a bit of a different way. With variable displacement rotary actuators, the volume can be changed. There are some that have variable displacement, so you can actually change how much displacement is necessary. I don't have one to show y'all, I don't think. All we have are the motors in there. I don't think those are variable displacement. I'd show y'all exactly how that works. But the speed of any actuator depends on the flow capabilities of the entire system and the orifice size of the cylinder. That's what I was trying to say earlier. Okay? What is the flow capabilities of the entire system? If your on a job site and the only thing you've got is a little compressor that's about a foot tall that runs on gasoline and can only provide 60 psi of pressure, you're not going to get as much done as one that's bigger that's able to provide 120 psi, right? The flow capability isn't there. That makes sense? That's just your that is just your system pressure. When you're dealing with the orifice size, what we're talking about is, let's see if I can. All right, so art time. So here's your cylinder, and here's your port. All right. If I make that port 10 times bigger, that means my flow rate into that cylinder is going to be a lot faster, right? That makes sense. If I shrink it, it's going to reduce the amount of flow rate into that cylinder. Does that make sense? So it's kind of like going down 280 as the 8-lane highway it gets to, and then you get to a constriction where it's a 4-lane. Which one moves faster, the 8-lane or the 4-lane? The 8-lane, right? It gets that 8-lane. You can straight drive through that sucker faster than you can get through the 4-lane. Just to kind of give you another example of that. Any questions on this, guys? Now we cannot act, and we can, trying to throw too many words together, give me a second. We can estimate cylinder speed, but until we get it in field and in use, we actually tell you exactly what that cylinder speed is? No. So we can have estimated cylinder speeds. I believe this is actually in your little book. Everybody got one of these, by the way? If you don't, you can come up and borrow one of mine. Oh, where is mine? There's. This particular one is on page, well, you have hydraulic cylinder speeds on page 17 and pneumatic cylinder speed. Well, if you start looking through this book, you can go on forever. So let's just look at cylinder speeds for hydraulics. So what are they looking for? They're looking for the size of the piston, the size of the rod, and how much flow you have for gallons per minute. Okay, these are just standard ones. Okay, these are just standard ones. With pneumatics, another thing you might have to look at, I'm sorry, let's get back up. One of the things you can look at as well are the size of the valve diameters, because that's going to affect it too. Why? It maintains how much fluid is able to enter and exit at one time, right? Why is that important? Well, because the more or less that can move, the more or less your cylinder will move. That makes sense? And you also have to understand that These are approximate speeds under average conditions. And all conditions are not average, right? Not to mention, over time, you're going to have things that change minutely until you put a brand new piece in there and go, oh my gosh, I didn't know what this thing was doing, right? I didn't know how gunked up this thing was, or I didn't know that this thing was that wore out. All things deteriorate with time. I can get the right words to come out of my mouth. So since the volume of an actuator cannot be changed once chosen, the speed of it is controlled by the speed of the fluid. It's given two ways. You have standard cubic feet per minute for pneumatics. And again, that's going to be mostly imperial standard. Why do I make sure that y'all know that that's imperial versus metric? Because imperial is only accepted here in the US and two other countries outside the US, if I remember right. And I think England is the only other one that may be a superpower that tends to still kind of sort of use imperial. They're mostly switched to metric. That and they have their own version of imperial. Don't ask me why. So standard cubic feet per minute. The feet is what clues you in that that is imperial, not metric. And then you have gallons per minute, which gallons again is imperial, not metric. So that would only be something applicable to us. Just going to ahead and clarify that right now. If you end up in some place like Germany working on something else, it will not give you SCM, will not give you the standard cubic feet per minute or the gallons per minute. It's going to give you something in metric. And if you end up anywhere else in the world that does not use imperial, which again I think is like us and two other countries. The flow is primarily controlled by the pressure source because the pressure source is what causes the flow. So think about it like this. I know y'all mostly taking electronics, right? Your voltage determines your current. Why? Because your voltage determines your current. Yeah? Same thing here. Your flow is controlled by your pressure source. Your pressure source is your voltage. Your flow is your current. Does that make sense to everybody? So the flow can also be controlled at flow rates to create a below pressure source by flow control valves. In other words, we can put other things in the circuit to help lower the voltage, right? Lower the pressure, but still keep the same current. Those of you that remember DC, that is called a series circuit. Controlling the speed. So the speed of the cylinder is controlled by the flow rate of the fluid actually entering the cylinder and the area of the piston. In other words, the bigger the piston, the more area that has to be covered. The speed of a motor or rotary actuator is controlled by the fluid flow rate entering it and its displacement of it. So in other words, how much area is inside that motor is going to be what is determining the speed of the motor. Okay? What's something else that might determine the speed of the motor? Y'all have all had to deal with this with some of these motors because these motors are not exactly brand new. So what was one of the problems y'all had with the motors that we have in lab? Well, exactly what I mean is the fact that, yes, you had all this air moving through that motor, but it wasn't about the displacement that did not get the motor started. It was about what? Pressure and compression, right? You know, the motors aren't exactly brand new, so the seals are not exactly, strongest in the world. So if you don't put enough pressure that it builds up faster than it can discharge out through the muffler, Y'all know what I'm saying? That's why y'all ended up with a stalled out motor, and some of y'all had to manually turn it over to get it to move. And then once you added more pressure, all of a sudden that motor was able to turn over by itself, right? So that's something else you have to kind of take into consideration with things like that, is that, you know, eventually seals do break down. All things break down with time, right? All right. So all speed calculations are estimations due to the fact that you have losses in the system by piping, fitting, and porting through the valves. Flow losses caused by a loss in pressure, which directly affects the output force. You saw some of that in lab. So if you want to go for true accuracy, you need to know the actual actuator's inlet flow rate. This is the point where you would have to use a what? Flow meter. You would have to use a flow meter if you wanted the actual flow rate. Sorry, is everybody good? Anybody need a second? All right. So here's some estimated cylinder speed equations. Again, I think this is in the book. Travel speed of a hydraulic cylinder piston. Got it in a couple places, I think. So you have 231 times your gallons per minute. This is actually somewhere in the book, but I can't remember which page it's on. So it's divided by 12 times the net area of the cylinder. With pneumatics, you're dealing with the same thing, except it's the actual cubic feet per minute divided by the piston net area. Full extender retract time, you have the cylinder volume divided by the actual cubic feet per minute times 28.8. No, I do not know where they got that particular number. And then you have gallons per minute times 231. Again, I don't know where they've got that number from. That is kind of like asking where Pythagorean got his theorem from. Who decided a squared plus b squared equals c squared? Why not x squared plus y squared equals z squared? There's 1,001 ways that could have gone. We ended up with a plus b equals c. All right, everybody good? All right. Flow control circuits, you have meter in, meter out, bleed off. These meet varying flow control demands for systems with positive and negative loads. We're about to get into those. So this is where we talk seriously about meter in versus meter out. Meter in. This should only be used for positive loads. What do we mean by positive loads? You don't have the ability to move under a negative load. So in other words, this does great for pushing, or if you must, you might be able to do some pulling, but for the most part, this thing has no ability to pull. It can push all day long, but it cannot pull. Okay? And even then, it's a slow push. Meter in is not the most trying to talk too fast again. Meter in is not the most desirable configuration because it only supports a positive load. It only supports the push. Does that make sense? When we get to lab, I'll actually show y'all meter in versus meter out. There's one particular lab I was gonna let y'all, I was gonna put up on there for y'all, show y'all what I mean by positive versus a negative load. So the prime mover is always operating against the maximum pressure setting of the system relief valve. We'll talk about what that means, or I'll show you what that means in a second. All right, so the main thing you need about meter in is that the flow control valve is between the pump and compressor and the inlet of the actuator. I'll show you what that means here in a second. And it should only be used for positive loads. That's the biggest thing about meter in. It should only be used for a positive load. The biggest thing I can tell you is it's a slow pressure instigator. All right. Does that make sense to everybody? I think all of y'all have dealt with meter in versus meter out so far, but we'll. So this is a meter in circuit. So what do you notice is the fact that your check valve, right? When you apply pressure, the incoming pressure, it goes through the constriction. It can't go through the check valve, right? So that means that this cylinder right here is going to fill slowly, but all the pressure right here is just going to dump straight out. Does that make sense? So it has no pushback on that cylinder to ensure that it rises slowly. The only reason it moves so slowly is because of why? Because it takes that much longer for the pressure to build. Okay, so going back to my earlier example the other day, if this is a movie theater, I have dumped every last patron out of their seat and shoved them out the door. What does that leave me with? It leaves me with an empty stadium, right? And it means that everybody else has to trickle in to fill up the seats. Does that make sense? That is meter in. Now then, why won't it support a negative load in this case? Well, let's take a look. If I start putting pressure back on the bore, where's all my pressure going to go when it comes back up this pipe? Is it going to try and go through the constriction, or is it going to dump its way out the check valve? It's going to go through the check valve, right? What's going to be the path of least resistance is that check valve, right? So the pressure will instantly jump up into the check valve, dump its way out, and go to and just be vented. That's why these cannot support a negative load. Okay? These cannot support a negative load. Meter out. So this, I won't bore you too much with this. It provides very accurate control for positive or negative loads, especially when you have it on both sides of a double acting cylinder. Okay? Easiest way I can say that and the fastest way I can say that, because it's easier to show you through picture. So again, this is my stadium seating right here, right? With meter in, what did we see? With meter in, we saw all the air dump out, right? And a slow fill up. With this one, whenever I start applying pressure against the board to extend the rod, where's the air got to go to get out? Is it going to try and go through that check valve? Oh, wait, it can't. Why? Check valve's facing the wrong direction. Does that make sense? So it's got to go through constriction. And again, constriction is just like a gate at any sporting event or movie theater, right? Only one person through the gate at a time. Or if you open the gates further, you might get more. But you control the amount of people moving through that gate. Same thing for meter out. You control how fast the air in this cylinder is going through that constriction. If I have it on both sides, that means that whenever I start to retract, I would control the air going out through retraction. But as it is, whenever I tell it to retract with it just once, with 1 meter out valve, that means that all my air is just going to come straight through this guy right here. And the only thing controlling my retraction is the air leaving this and any restrictions I have on this side of that line. If I don't have restriction, it will move back at a faster pace than it was able to extend. Does that make sense? But meter out is all about controlling the outflow, not the inflow. Meter in was about controlling that inflow, correct? Y'all see that? Meter out is about controlling the outflow. Does that make sense to everybody? Yes, no, maybe so. So with meter in, I have an empty stadium to fill every time because everything dumps out at once. With meter out, I have a stadium that people are leaving, but at the same rate, people are coming in. Does that make sense? So I can only have as many people leave as people come in. The pressures match up. Does that make sense? That's why meter out controls both a positive and negative load. Operation of basic flow related circuits. So if you have something called the bleed off, the outlet of the flow control is directly connected to the reservoir or the exhaust. That particular measure of flow is diverted to the reservoir, to the exhaust, while remaining flow rates operate the actuator. Essentially, everybody knows what a bleed-off valve is, yeah? What's it meant to do? It's meant to bleed off excessive pressure. In other words, we know that there's excessive pressure on this particular system. We need to make sure that that does not exceed the pressure that we need. So essentially, that's exactly what it does. All right. So deep into this, simply because I think that most of it just starts getting redundant. If you're going to use if you're going to be selecting the cylinder, which that's generally the engineer's job, not yours, but if you have to, you have to determine in pounds the force needed, excuse me, the force needed to do the job. Then you add 25% extra for friction and allow the actuator to move at reasonable speeds. So what do we mean by that? Well, what happens over time to that force? What do you think? It's going to slow down. It's going to become less. Why? Because time wears on all things. So you oversize it just like everything else, right? You oversize it for the job it's got to do. Yes. You oversize it because eventually it's going to become undersized. Does that make sense? You have to determine how much pressure will be used and maintained. So in other words, if every one of you go in there and start trying to run a circuit at the same time, what's going to happen to the total system pressure? It's going to drop, right? So what does that mean? Well, that means that there's going to be less pressure for everybody to use. So how much air pressure or how much pressure in the system can be used and maintained? You have to look at worst case and best case scenarios with this, guys, because you're going to have to also set up things like bleed off valves and things like that to handle any excess pressure in case, you know, the rest of the system's not working. This is the only machine that's working that day, right? That's a best case scenario. Worst case scenario, every machine's working that day and everything's sucking off power. So how much power do I have and how much can I maintain of that? Does it make sense? Divide the required force by the PSI to get the required area power factor. You can use the formula that's listed here, but it's much easier to use this table right here. I'm trying to remember what page this is on as far as power factor goes. It is in here somewhere. I've just got to dig it out. I'll look for that in a minute. So what they are showing you is the bore diameter and the power factor you can use with it, and it gives you the ability to look at what you're looking at. So the estimated force needed is 900 pounds. Air pressure to be used is 80 psi. So what they set up is 80 psi times your power factor equals 900 pounds. Divide 900 by 80 and you get 11.25. But we want to oversize it, right? We don't want to undersize, we want to oversize. So we start looking at the next place up. So we're stuck right here between 8.3 and 12.6. We don't want to go down, we want to go up, so we go up to a 4-inch bore. Does that make sense? So I'm just kind of trying to go fast and easy here, guys. We'll review anything needed on this for the test before test 2. So cylinder inches, this is table 4.1 in your book. Pneumatic cylinder data, but it's showing you the cylinder inches in diameter, the rod inches, cap end, rod end area, which we've seen this kind of table before in our little books. And this is telling you exactly what PSI you can use with these, what is going to be your force out. Again, this should all look very familiar because we've seen it on the pages 15, 16, and 20. 20 is the pneumatic force. Okay. What you don't generally see is the displacement per inches of piston travel. We don't really look at that too much. Just a secondary table. So if you're selecting a valve, they must be able to handle the pressure and flow required by the actuator. What do we mean by that? Well, if it's undersized as far as pressure goes, you're going to do what? If you undersize for pressure, you're going to blow your seals, right? You put that sucker in, it's undersized, you're going to blow the seals faster than you can say, oops, right? Again, this is a lot of the stuff the engineers look at. The valves are usually rated in a CV or KV. This is the flow coefficient, which is an indication of the volume of fluid the valve can pass. The more fluid the valve can, the larger the rating, the more fluid it can pass. But again, that's more of the engineering side of some of this, not the maintenance side of it, which is where we are, right? So if you look right here, it tells you the response time. It's telling you what it is, as well as the standard cubic feet per minute at 100 psi. So just something y'all can kind of look at. The CV that is needed depends on the volume of the actuator. And this is actually a formula you might want to look at and bookmark in the book on page 27. On the little book, page 27, guys. And I can pretty much guarantee you might want to dog ear this page because it can and will be used on test material. So you might want to go ahead and have it on hand. Page 27. It should look like that page. Okay, it might be another page or two forward. Well, they might have updated the book from my original version, so I'm page 20 on y'all's. I'm sorry. You have to remember mine is over a decade old. So they did a little updating on these in the last couple of years, apparently. That's why mine are dog-eared like crazy, because I use these. These are a very popular little book. So page 20, you might want to dog-ear it, guys. Y'all know what I mean by dog-ear, right? Bend it down. So this is where the area of the cylinder is in inches squared. You have the stroke of the cylinder in inches. Okay, so looking at your formula, you have your area, your stroke. A is your compression factors and constants. All right, so if you look in your book, that 5 psi that's in the center of it, highlight that, because that applies for most applications. That is a 5 psi pressure drop. In other words, that's your system pressure drop of 5 psi, so it's not a highlight or circle the 5 psi column, because that is the most common pressure drop of systems. What that means is that most valves and stuff, you will you'll have generally a 5 psi pressure drop from system pressure. Compression factor is on here as well. And you have time and stroke. So we're going to look at one real quick. So pressure at the inlet of the cylinder is 80 psi when the cylinder is in motion. Okay. So if we look for the inlet pressure in your little booklet here, you're looking for 80 psi. And you look over here to where it says it's a 0.048 pressure drop constant. And then we look at the fact that it's also a 6.4 compression factor. Gives you the cylinder has a 3.5 inch bore and a stroke of 6 inches. And an extend time of 0.75 seconds. So if you look at 80 psi and just start carrying it across, you have a compression factor of 6.4 and a pressure drop of 0.048. Okay. They give us in the problem a 3.5 inch bore and a 6 inch stroke and an extend time of 0.75 seconds. So this is the required flow for operating this particular cylinder is 0.78. I said all that for that. We won't really go about talking about without the tables, and I think we covered some of the cylinder symbols last time, didn't we? Yeah. They're as numerous as they come because why? Well, because they're all dependent upon what people need, how you need to configure them, right? All right, so before we get to motors, we will stop for the night.